Assalamu alaikum friends. I'm Taqdees Siddiqui with Computer Graphics, a course being offered by Virtual University, Government of Pakistan for the students of Bachelor's in Computer Science. As we are inching towards the finish, we'll be talking about more advanced topics. Today is our 40th lecture, and today we'll be discussing another fascinating, exciting topic from contemporary computer graphics, and that is fractals. So without wasting further time, let's get along with it. Let's try and define fractals first. Fractals are geometric patterns that are repeated at ever smaller scales to produce irregular shapes and surfaces that cannot be represented by the classical geometry. We have been working with Euclidean geometry for quite a while. In fact, Euclidean geometry has been used to come up with representations of almost all the man-made objects. But fractals are different in the sense that Euclidean geometry does not suffice representation of these patterns. These are such patterns which are self-similar, and as we move into or zoom into these patterns, we continue to discover infinite levels of detail, with the self-similarity being consistent. Fractals are used in computer modeling for irregular patterns and structures in nature. There are certain structures that are existing in nature and they cannot be completely described or described with complete detail using Euclidean geometry. But these patterns can always be defined and described by fractals. So that is where fractals are going to come along and help us describe such patterns which are existing in nature and cannot be described completely using our existing classical geometry. As we'll take a look at some of the examples, the idea and the concept would become clearer. According to Webster's dictionary, a fractal is defined as being derived from the Latin word fractus, meaning broken or uneven. Any of various extremely irregular curves or shapes that repeat themselves at any scale on which they are examined. So, dictionary definition of fractals would be that it is a word derived from a Latin word, fractus, which means to break or broken. And this is actually targeted towards such patterns which, when observed or examined at a micro level, going into the details, we keep looking into patterns which are similar to the main macro level pattern. So we look at an object, and as soon as we start walking into the depths of it, we start realizing that the smaller components that are joining hands together to form that bigger whole, they are actually similar in shape to that bigger whole. And this self-similarity can be examined at infinite number of levels theoretically. Mandelbrot, which is the discoverer of the fractals, he gives two definitions. He says, I coined the term fractal from the Latin adjective fractus. The corresponding Latin verb frangere means to break or to create irregular fragments. This is the first of the definitions given by Mandelbrot. He was the one who actually came up with this discovery, the fractals, these irregular shapes which are really exciting and fascinating in nature because of the very fact that they have infinite levels of details, and at every level of detail we get to know that this is actually similar to the preceding level. So similar patterns repeating themselves within each pattern and going into the depths of those levels reveals that all those patterns are similar to each other. Theoretically speaking, they are strictly self-similar. Practically, we might be talking about some statistical similarities. We'll get to know the difference between them in a short while. Every set with a non-integer Hausdorff-Basikovich dimension d is a fractal. However, not every fractal has an integer d. A fractal is, by definition, a set for which D strictly exceeds the topological dimension D caret, which is D raised to power something. So this is another definition by the same author, the discoverer of fractals, Mandelbrot. But in order to understand this definition, we'll have to do a little more. So before just analyzing and discussing the definition, I would go a step further, and then we can get back to this definition again. We have mentioned the Hausdorff-Basikovich fractal dimension. In order to be able to understand and make some sense out of the last definition, the second one from Mandelbrot, we'll have to understand what is this fractal dimension given by Hausdorff-Basikovich. To understand the second definition, as I said earlier, we need to be able to understand the fractal dimension. So first, we have to understand how to calculate the dimension of an object. Next, we consider some three different objects which are going to help us understand the concept of this fractal dimension. We are already familiar with the concept of single, one dimension, two dimension, and three dimension. But when we are talking about fractal dimension, we mean something different from that. This understanding is kind of an intuitive understanding of dimensions rather than what we have already come to know discussing the coordinate systems. The one-dimension coordinate system, the two-dimension coordinate system, and the three-dimension coordinate systems. This is slightly deviating and different from that idea. Let's discuss it one by one. The three objects that are going to help us start with a line. We are familiar with the concept of a line. A straight line we are pretty much comfortable with. We have understood the concept geometrically, and we have been drawing lines, making use of certain algorithms in our computer graphics course as well. As you can see, the line is broken into four smaller lines. Each of these lines is similar to the original line, but they are all 1/4 the scale. Now, this is the idea of self-similarity. Take a look at this line segment that is in front of you right now. From end to end, from starting point to end point, this is one straight line. What we've done is that we have divided it into subparts. Precisely over here, we have made 4 parts of the same line. Now, each of these segments, or the sub-segments of this line segment, they are similar to the original line segment. The original line segment is a straight line, having a start and an end point, and same is true for each of these segments. The first segment, which makes use of the starting point of the main line segment and has the first division marked at 1/4 of the length. Second line segment starts at the 1/4 of the length and ends at the middle of the line, the original line segment. And then in the third quarter we have the third segment, and in the fourth quarter we've got the fourth segment. Now, each of these 4 segments is similar to the original line segment. So we say that these line segments, the 4 that we have divided the original segment into, they are self-similar. The original line segment and the subsegments, they are similar to each other. So there is the concept of self-similarity materialized as soon as we divide this line segment into multiples. Next object that we take is a square. The square that you're going to look at now has been broken into smaller pieces, each of which is 1/4 the size of the original. And in this case, it takes 16 of the smaller pieces to create the original. Take a look at the square. As we discussed in case of that line segment, this square is also cutting similar looks. What we've done is that we have come up with a smaller segment, which is a smaller square, which has got its side length equal to 1/4 of the original square's side length. Right? So we say that if the original square's side length was 4, the side length for this smaller square is 1. Or if it was originally 1, now it is 0.25 or 1/4 or 1/4. And now we see that we require about 16 smaller squares in order to define this bigger square. The square, original square, has been divided into self-similar 16 smaller squares. Remember that the scale that we've used is a quarter. If original was a unit, the smaller is a quarter of the original. So 1/4 वाला आइडिया जो है वो अभी भी हम लेकर के चल रहे हैं. लाइन सेगमेंट के केस में भी हमने ये किया, उसके 4 हिस्से किए, ईच पार्ट वाज अ क्वार्टर ऑफ द टोटल. और स्क्वायर के केस में भी हमने जो स्मॉलर स्क्वायर्स बनाए हैं उनकी साइड लेंथ जो है वो अ क्वार्टर ऑफ द ओरिजिनल है. बट रिजल्टिंगली यू सी दैट स्क्वायर को कंप्लीटली डिफाइन करने के लिए जो कंपोनेंट्स हमने सब कंपोनेंट्स यूज किए हैं वो हमें 16 चाहिए. द नेक्स्ट that we are going to take up is a typical of 3-dimensional objects, the cube. As with the others, the cube is also broken down into smaller cubes of quarter the size of the original. It takes 64 of these smaller cubes to create the original cube. How? Just take a look at the picture. That's the cube that we are talking about. When we were dividing straight line into the subcomponents or self-similar parts, we required 4 of them. जो ही हमने square की बात की, we required 16 of those. In case of cube, as we are moving into the third dimension as well, we require 64 of such smaller cubes. Basic idea has been the same. In case of square, we came up with squares of side length quarter of the original. In case of cube, we have come up with the cubes, smaller cubes, that are having the side lengths, each of 3 sides lengths, quarter of the original. And in this case, we require many more smaller cubes to define the whole. So 64 smaller cubes would suffice describing or defining this bigger cube. By looking at what we have just seen in case of the straight line, the square, and the cube, we tend to see a pattern, right? You can see it on your screens now. In the first case, we have 4 is equal to 4 raised to power 1. Can you guess what these numbers are signifying? Well, of course, 1 makes some sense. That straight line was probably an object from 1 dimension. In case of square, we have 16 is equal to 4 raised to power 2. Aha, it now starts making a little better sense. There were 4 segments in case of the straight line, and there were 16 smaller parts in case of square. 16 squares was what we divided the bigger square into. And what we did was, we used 1/4 of each side length to define the smaller squares. So this 4 is also now making sense. And that square happened to be from the 2-dimensional word. Fine. And what about the third relationship? 64 is equal to 4 raised to power 3. 1/4 has been our scale for the smaller cubes, and we were talking about a 3-dimensional object, and the total number of smaller cubes that required to completely describe that bigger cube were 64. 4 raised to power 3. Now this gives us the equation n is equal to s raised to power d. You'll be able to make sense out of it now. Where this n is the number of small pieces that go into the larger one, s is the scale to which the smaller pieces compare to the larger one, and d is the dimension, right? Let's go back. N is equal to s raised to power d. Now it is gelling in, right? N gives us the total number of smaller pieces that are required to suffice the bigger object. And when we compare the smaller objects with the bigger objects, the scale is that of 1/4, so that is given by s, and d is giving us the dimension. Now let's solve for d in the previous equation, and we find that d can be described as d equals log n over log s. In the previous relation, if you take log of both sides and then you simplify, then rearranging the terms, you get d is equal to log n over log s. Now this dimension is the Hausdorff-Basikovich dimension. the fractal dimension that we wanted to calculate and find out. Now, in order to make a better sense of the basic concept of fractal, let us make use of another example, and this is called Koch curve. We have talked about fractals being such geometric patterns that have the concept of repeating themselves at every next level of detail, and every next level of detail reveals that the next level of detail is self-similar to that object. Every next level of detail is similar to the previous one. You look at the whole object and you develop the sense of the shape of the object, and then you walk into the detail, the next level of detail, you zoom into that object and you start realizing that every part of that object is actually comprising of the pattern which is quite similar to the one that the whole object is. The overall picture is whatever the original picture was, the smaller components were similar to that. We have just seen the simpler examples in case of a straight line decomposed into 4 segments. Then we talked about a square decomposed into 16 smaller squares, and then the cube decomposed into 64 smaller cubes. And each one of those smaller cubes was similar in shape to the bigger one. And that was the concept of self-similarity that we just observed up to one level. We are going to go beyond that as well. And in order to better understand it, we are going to take an example. And this example is the Koch curve. Euclidean geometry is the geometry of lines, planes, circles, etc. It's simple and it works. And for a long time, mathematicians thought that it was a reasonable representation of nature as well. Later on, they came to know that there are certain things that are existing in nature that the Euclidean geometry alone cannot help represent completely. We can have lines, we can draw circles, we can draw even curves, squares, we can have the concept of planes containing triangles and things of that kind. But there are certain objects that exist in nature which are not man-made objects, and they cannot be described completely using the Euclidean geometry. But earlier, people thought that Euclidean geometry was simply enough to model and represent all that exists in nature and can be drawn. So, after this discovery, people came to know that the classical geometry was unable to describe certain curves and surfaces which were possible to exist in nature or possible to draw. Now, this was the initiating point of getting to know what can describe such patterns if Euclidean geometry fails to do so. And that is where Mandelbrot came along. Now, how hard can it be to draw a curve? We have learnt and we know we can do it. But let's attempt to describe and get to know how Koch curve can be built. Let's start with a very, very simple picture. That's a triangle, and each one of us is pretty much familiar with the triangle. Let's start drawing using this very simple curve. A triangle with 3 equal sides. For the moment, let's presume that the side length is a unit. कह लीजिए मीटर है, कह लीजिए फुट है, कह लीजिए इंच है, whatever. But let's say each side is 1 unit length. So the total length of this picture would be 3 units. Let's draw a triangle, and if we say that the side length is a unit, total length would be 3 units. Next step that we do is something very interesting. We annex some new triangles which keep the dimensions same, but measurements are different. We come up with 3 smaller triangles which are having their side length equal to 1/3 of the original. So originally हमने कहा था कि हमारी side length जो है वो 1 है. तो ये जो छोटी ट्राइंगल जिनकी हम अब बात करने जा रहे हैं, ये हमने कहा कि ये हर एक साइड इनकी जो है वो 1/3 यूनिट के ऊपर मुश्तमिल है. सो नई ट्राइंगल्स की साइड लेंथ इज 1/3. ठीक है. नाउ हैविंग पुट दीज 3 triangles in the middle of the 3 sides of the original bigger triangle, what we come up with is this kind of a picture, the David star-like picture. But we do another step in order to make this a continuous curve. जो हमारी सबसे पहले ड्रॉ की हुई बड़ी ट्राइंगल है, उसके जो एज का पार्ट इस ट्राइंगल, छोटी ट्राइंगल के बेस पे दिखाई दे रहा है, इसे हम इरेज कर देते हैं. So as soon as we erase that, we get to see a different picture, right? Now this would be a 6-cornered figure, a star-like shape. लेकिन आप ये याद रखिए कि हमने इसको जनरेट कैसे किया है. ओरिजिनल ट्राइंगल हमने बनाई, फिर उस जैसी ही लेकिन 1/3 साइड लेंथ वाली 3 ट्राइंगल्स बनाई, जिन्हें हमने उन तीनों साइड्स के ऊपर मिडल में पॉइज कर दिया, और उसके बाद जो बेस लाइंस थी उनको हमने इरेज कर लिया, मिटा लिया, ताकि हमारे पास कॉन्टिन्यूस पिक्चर आ जाए. नाउ दिस वुड बी आवर नेक्स्ट स्टेप. बट सी, अब ये जो हमने नेक्स्ट स्टेप किया है, इसमें लेंथ पे क्या इफेक्ट हुआ होगा. ओरिजिनली हमारी लेंथ थी 3 यूनिट्स, ठीक है. नाउ हाउ मेनी मोर यूनिट्स हैव वी एडेड? लेट्स सी, कैन वी काउंट? वेल, चूंकि नई ट्राइंगल्स की साइड लेंथ जो है 1/3 है, तो इस सूरत में क्या होगा? व्हाट वी हैव एडेड इज 2 साइड लेंथ्स फॉर ईच स्मॉल ट्राइंगल. सो क्या दिखाई देता है? That on each side we have added 2/3 of the length, 2/3 of length or 2/3 unit of a length, that is being added on each side, and we've got 3 of those. क्या होगा? ओवरऑल लेंथ जो थी उसमें क्या ऐड हो जाएगा? 3 times 2/3? No. Be a little careful. अभी मैंने लास्ट स्टेप क्या बताया था कि हमने जो बड़ी हमारी ओरिजिनल ट्राइंगल है, उसका जो पार्ट, उसके एजेस का जो पार्ट इन नई छोटी ट्राइंगल्स की बेस पे आ रहा है, उसको हमने इरेज कर देना है. तो जो है हम इसे इरेज करेंगे तो एक्चुअली वो वाला जो 1/3 पार्ट होगा वो तो इसकी कर्व की लेंथ में से गायब हो जाएगा ना. सो ओवरऑल तीनों साइड से 1/3 एक्चुअली ऐड हो रहा होगा. सो ओवरऑल लेंथ वुड बी इंक्रीज बाय ओनली 1 यूनिट. सो in this case, this modified curve will have length 4. So in this case, we have 12 edges and 12 points, and the length of the curve is now 4. The idea is to repeat the same process again and again and repeat it theoretically forever. Although we will not be able to do that practically, but theoretically the idea is to repeat this process of adding these triangles to the sides forever and ever. What kind of picture shall we get? See this? All we have done is कि हमारी जो प्रीवियस पिक्चर थी उसके अंदर जितनी भी साइड्स थी, हर एक साइड के ऊपर उस साइड की 1/3 साइड लेंथ वाली ट्राइंगल हमने ऐड की, और फिर वही पुराना तरीका जो ओरिजिनल नीचे जो ट्राइंगल थी जिसकी वो साइड बेस बन रही थी नई ट्राइंगल की, उसको हमने इरेज कर लिया, ताकि हमारा कॉन्टिन्यूटी ऑफ द कर्व जो है वो बरकरार रहे. एंड दिस वुड रिजल्ट इन दिस पिक्चर. सी, ऑल दैट वी हैव डन इज प्रीटी सिंपल. एल्गोरिथम हमारा कोई बहुत कॉम्प्लेक्स नहीं जा रहा अभी तक. We started off with a triangle. We added 3 triangles for the 3 sides. In the next step, for every edge, we added another triangle of 1/3 of the side length. And this process is repeated again and again and again. In the next step, we'll see that we'll have something like this appearing. Same process repeated yet another time. And we'll realize that the overall length of the curve would have become 5.33333 so on. अब आप ये प्रोसेस रिपीट करते चले जाइए. अगर हम इसको infinitely many times रिपीट करें, what would be the resultant? Theoretically, dimensions would go to infinity. But we are going to have a finite length, and this is a very interesting part. That overall length of the curve would be finite, but it is going to have infinitely many levels of details built into it using a very simple algorithm. Yet another step. We have come up with another different looking curve, and the length has been increased. This has been increased to 12.6420 at the last picture level. As we continue adding these edges, the length of the curve increases. If we add edges forever, then length of the curve reaches infinity. But the whole curve nevertheless covers a finite area. Theoretically speaking, the length would be touching infinity. If we continue the process infinitely many times, we repeat it. But practically the curve is going to be a finite one. It is not going to cover infinite area. But as the theory says, practically अगर हम इसको repeat कर पाते हैं जितने levels तक, हर next level पे जाने के बाद हमें greater level of detail मिलेगी. That's the basic idea of the self-similarity that is exploited by this picture. The curve is infinitely detailed. No matter how closely we zoom into the image, it always shows up more detail. So no amount of zooming in is going to result in saying that, okay, here the maximum detail has been reached and now we cannot have more detail available. We are going to talk about this self-similarity in a little further detail. Having seen these examples, what do these mathematical curiosities have to do with the real world? Well, everything, as it turns out, has got to do with it. Such objects, they turn up all the time in our real life and natural world. Can you recall any? Can you think of such objects that exhibit this kind of self-similarity? A very native example is that of a fern. If you have traveled in the countryside, northern areas में अगर आपने travel किया होगा, you would have seen that there are so many different types of ferns available that are growing on the sideways. Take a look at any of those plants. The fern, as you look at it, it's a beautiful picture. This object, when closely observed, reveals that it has got the same patterns, the self-similar patterns repeated at the next level of detail. We are going to take a look at this example. The next figure is that of a standard fern that we are going to make use of. We will see that the overall theme of repeating leaves is there. Each smaller leaf looks similar to the larger leaf at the previous level of detail. Look at the picture at the left side. This is one big leaf. That's a fern. But as soon as you zoom into it, you realize that each part of this leaf is actually comprised of a pattern which is very much similar to the original plant. कोई एक पत्ता उठा के देख लीजिए, उसकी शक्ल आपको दिखाई देगी जैसी लेफ्ट साइड पे दिखाई दे रही है. As soon as you look at each sub component of it, उसके अंदर भी आपको वही पैटर्न जो कि मेन प्लांट का है वही रिपीट होता हुआ नजर आता है. और यही नहीं, इससे अगले लेवल पे जाने के लिए जब आप इसके अंदर फिर मजीद स्मॉलर कंपोनेंट्स देखते हैं जो कि सिमिलर हैं ओरिजिनल फर्न से, एंड यू रियलाइज दैट दे आर एक्चुअली अगेन डिफाइंड इन द वेरी सेम मैनर. मगर ये सन्नाई कुदरत की है. ऑल्दो इन दिस केस वी कैन नॉट गो टू इन्फिनिट लेवल्स ऑफ डिटेल्स, लेकिन ये वो चीज़ें जो हमारे लिए तहरीक का बायस बनती है टू गेट टू अंडरस्टैंड दिस कॉन्सेप्ट एंड देन एक्सप्लॉयट इट इन द फॉर्म ऑफ दीज एक्साइटिंग फिगर्स कॉल्ड द फ्रैक्टल्स. जब हम डिफाइन करें फ्रैक्टल्स को और एक्चुअली रिप्रेजेंट करें, वी विल बी एबल टू गो अप टू ग्रेटर डिटेल्स. इन केस ऑफ फिजिकल फर्न, there is a limit. You ultimately end up with the petal which is not subdivided into self-similar patterns. लेकिन उस petal के ऊपर आप गौर करें तो आपको built-in जो structure दिखाई देता है, जो kind of engraved है, वो बिल्कुल वैसा ही है जैसा original fern का है. So looking at it a little closer, we can see that those small leaves, they are made up of even smaller leaves. We take up the smaller leaf, we look at it, the subcomponents, they are also leaves and are organized and arranged in the very same manner the original fern is organized. Go a step further, you get to see another smaller fern making up the bigger fern. Of course, in reality, a fern does not have a smallest leaf, which is at infinity, though we are sure that every fern aspires to be like that one. Whichever fern you pick up would be of the very same kind. As I said earlier as well, that at the smallest level, the leaves that we find, they also are engraved with patterns which are similar to those of the original fern. What is interesting in it, that the program to generate this image is only a few lines long. We can make use of the concept of recursion as well as iteration to come up with these patterns. Before we can move on, let's talk a little about the fractal geometry. We have already established that the Euclidean geometry is unable to help us in representation of these objects, like the fern that we have seen, or like the Koch curve that we earlier on built. This is the fractal geometry that helps us represent these. Let's take a closer look at it. Almost all geometric forms used for building the man-made objects, they belong to Euclidean geometry. They are comprised of lines, planes, rectangular volumes, arcs, cylinders, spheres, etc. These elements can be classified as belonging to an integer dimension, either 1, 2, or 3. This is an understanding that we've already had. We have talked about the primitives that require only one dimension. We have talked about those that require 2 dimensions, and then those that require 3 dimensions. But that's all about it. We have been playing with the Euclidean geometry with these 3 dimensions only. This concept of dimension can be described both intuitively and mathematically. Intuitively, we say that a line is one-dimensional because it only takes one number to uniquely define any point on it. If we talk about some line, and we talk about a point on that line, describing that point, knowing the line endpoints, is pretty simple. We can start from the starting point, and we can give a distance d that point is lying away from that starting point. So that one value, one integer, that suffices. And that's enough to describe that point on the line, even if that line happens to be a curve. We know how the curve is formed. We know the starting point. The 2 endpoints are known. From the starting point, at what distance that point lies, we specify that, and that would be one value giving us the required information. That one number could be the distance from the start of the line, as we said. Now, this applies equally to any circumference of a circle as well, or the boundary of any other object, because we can always have a starting point for it, and we can always measure that distance, that the point of interest is lying away from the starting point. Take a look at this picture. We're talking about a point A on a curve, and we can tell that it is at distance d from the starting point. Enough of information. A plane is a 2-dimensional, since in order to uniquely identify any point on its surface, we require 2 numbers. Now, there are many ways to arrange the definition of these 2 numbers, but we normally create an orthogonal coordinate system. Look at this illustration. We're talking about a surface or a plane. Well, we can have lines which are orthogonal to each other, and these grid lines, they can help us come up with those 2 numbers that would be sufficient or enough to specify the location of a point A on this plane or this surface. Let's call them D1 and D2, and these 2 would be enough to tell where the point A would be lying. The volume of some solid object is 3-dimensional on the same basis as we have seen in the last example, where we required 2 numbers. Now, it takes 3 numbers to uniquely define any point within an object when it is a 3-dimensional object. Those 3 points, those 3 values, those would be actually given as the distances along the 3 axes. In our coordinate system, x, y, and z, how far do we have to travel along x, how far do we have to travel along y, and how far do we travel along z before reaching our point of interest A in the 3-dimension. So if this is a point somewhere in the cube, d1, d2, d3 would be required and would suffice specification of the point A. Any point A on 3 dimensions can be uniquely represented by the 3 numbers. Typically, these 3 numbers are the coordinates of the point using an orthogonal coordinate system, the one that we have already seen. A more mathematical description of dimension is based on how the size of an object behaves as the linear dimension increases. In 1 dimension, consider a line segment. If the linear dimension of the line segment is doubled, then obviously the length, which is characteristic size of the line, that would also have doubled. Simple enough. You have a line segment, you double the linear dimension, the length of the line, that is doubled. If you have a square and you double the linear dimension, the length of it, what would happen? What would happen to the area? Now think about it. Would it be doubled? No, it would be increased by a factor of 4. आपके पास एक स्क्वायर है जिसकी साइड लेंथ 1 है. What would be the area? 1 square unit. मीटर है तो स्क्वायर मीटर. अगर आप इसको 2 कर दें, डबल कर दें, what would be the area? Will it be 2? 2 times 2, 4. 4 square meters. So that's what the idea is. That if we have doubled the length in case of a square, the area, the characteristic size, which is the area in this case, would be increased by a factor of 4. In 3 dimensions, if the linear dimensions of a box are doubled, then the volume increases by a factor of 8. Now this relationship between D, L and the resulting increase in size S can be generated and written as S is equal to L raised to power D. Now keep in mind what these S, L and D are, right? Now this is just telling us mathematically what we know from everyday experience. If we scale a 2-dimensional object, for example, then the area increases by the square of the scaling. And this we have seen in our real life. And we're comfortable with this concept. But if we scale a 3-dimensional object, the volume increases by the cube of the scale factor. If our scaling factor is 2, we're talking about 2 raised to power 3 as the factor giving us the increase in volume of that object. Single dimension के केस में डबल करने से लेंथ डबल हो रही थी, फैक्टर ऑफ 2 से इंक्रीज हो रही थी. 2 डायमेंशनल ऑब्जेक्ट के केस में जो एरिया है वो इन टर्म्स ऑफ इन फैक्टर्स ऑफ 4 इंक्रीज हो रहा था. 3 डायमेंशन के केस में तब यानी फर्स्ट में डबल हुआ था सिंपली, सेकंड में स्क्वायर हुआ, थर्ड के अंदर वी आर टॉकिंग अबाउट द क्यूब. द फैक्टर इज नाउ the increasing amount that we use for increase in side length for a cube, for instance, that results in volume increase of a factor of cube. Now scaling factor, we take cube of it and that gives us the increase in volume of the 3-dimensional object. Now rearranging these, the expression that we are going to get for dimension depending upon how the size changes as the function of the linear scaling, that can be given as D equals log of S over log of L. In the examples that we've seen, the value of D is an integer which is either 1, 2 or 3, namely the dimensions depending upon what dimension we are going to make use of, and this relationship holds for all the Euclidean shapes. There are, however, many shapes which do not conform to the integer base idea of dimension giving above in both intuitive and mathematical descriptions. And that is, there are objects which appear to be curves, for example, but which a point on the curve cannot be uniquely described with just one number. If the earlier scaling formulation for dimension is applied, the formula does not yield an integer. There are shapes that lie in a plane, but if they are linearly scaled by a factor L, the area does not increase by L squared, but by some non-integer amount. And these geometries are called fractals. As we have seen earlier as well, in case of Euclidean geometry, things are pretty much mathematically describable. But for explaining the fractal geometry, we have to make use of the intuition, the intuitive idea, because these are such patterns which are different in the sense that we cannot completely describe them making use of the rules that we have built in case of Euclidean geometry. These are really different, and these are contemporary. We have only started talking about them during the last couple of decades. Before that, we kept thinking and believing that the Euclidean geometry was sufficing the requirements of describing and representing all the objects that exist in nature or all the man-made objects. One of the simpler fractal shapes is the von Koch snowflake. The method of creating this shape is to repeatedly replace each line segment with the following 4 line segments that we are about to see now. It's a very interesting pattern, the von Koch snowflake. And you'll see that it is really very easy to generate as well, just like the Koch curve. Just take a look at this. What do you see? 4 line segments which have been arranged in this manner. Just absorb this image. Now what we are about to do is something very interesting. The very way we played with the Koch curve, the same idea would be made use of or exploited over here in order to come up with von Koch snowflakes. This process starts with a single line segment and continues forever. The first few iterations of this procedure, they are shown in the next figure. Take a look at this. The leftmost is that simplest form that we started off with. उससे अगली line को देखिए. This is slightly different from the previous one, but I hope looking at it a little closely you'll be able to tell the similarity. Each edge of the original curve that we started off with, the first line segment, that has been replaced with patterns that are similar in shape to the original line segment. The 4 segments, they joined hands together to form the leftmost line that we are seeing, that curve. Each edge, the first, second, third and fourth, have been replaced with smaller but similar in shape line curves. These curves are giving rise to a different shape now. At the next level, towards the even right, you would see that the same pattern has been repeated on each of the edges subsequently. You go a little further and you see yet another one. पिछले वाले लेवल के ऊपर हर एक लाइन सेगमेंट को फिर वैसे ही मगर छोटे स्मॉलर स्केल्ड लाइन सेगमेंट के साथ रिप्लेस कर दिया गया. The one that generates the pattern that we started off with. So we start off with a very, very simple pattern, 4 segments, and then we continue to replace each of those subsegments with similar, smaller segments. And that's what we get at the end of the day. This demonstrates how a very simple generation rule for this shape can generate some unusual properties. And that is what fractals are all about. Unlike Euclidean shapes, this object has detail at all levels. If one magnifies a Euclidean shape, such as the circumference of a circle, it becomes a different shape. Namely, it can become a straight line. If you zoom into the boundary of a circle even, you'll be able to see a straight line. But in case of fractal geometry, these objects, they have got inherently infinite levels of details built into them. So magnifying a fractal, more and more detail is uncovered. The detail is self-similar, or is rather exactly self-similar, theoretically speaking. Although, as I said earlier as well, that practically speaking, we may have certain statistical self-similarities defined, but overall look would be quite self-similar. Note also that the curve on the right is not a fractal, but only an approximation of one. This is no different from when we draw a circle. It is only an approximation to a perfect circle, because drawing a perfect theoretical circle is not possible making use of our display devices that we've got. We've got our limitations. At each iteration, the length of the curve increases by a factor of 4/3. Thus, the limiting curve is of infinite length, and indeed, the length between any 2 points of the curve is infinite. Now, this curve manages to compress an infinite length into a finite area of the plane without intersecting itself. Considering the intuitive notion of a one-dimensional shape, although this object appears to be a curve, with one starting point and one end point, it is not possible to uniquely specify any position along the curve with one number, as we expect to be able to do with the Euclidean curves, which are one-dimensional. Although the method of creating this curve is straightforward, there is no algebraic formula that describes the points on the curve. Some of the major differences between the fractal and Euclidean geometry are outlined in the next table. Before looking at that table, let's just recap it, that we have the basic idea that on some curve, in case of Euclidean geometry, we require only one number that gives us the distance of the point on the curve from the starting point, and that can be specified making use of that one number only. But the nature of fractals is such that you can never tell that what is that number in order to specify a specific point on the boundary of that curve. Although it looks like a curve, but it actually is a different one, different from the Euclidean curves that we have been seeing already. Because in this case, we are having infinite levels of details built into it. So as soon as we walk into the next level of detail, we find the same pattern repeated in there as well. And that is what makes it unique. A quick look at the table that is describing the differences between the Euclidean and the fractal geometry. Euclidean is, of course, the traditional geometry that we have been dealing with for hundreds of years. Fractal is the modern invention. Maybe only a couple of decades we have been through into it. Euclidean is based on a characteristic size or scale. In case of fractal, there is no specific size or scale. Euclidean suits description of man-made objects, whereas fractal that appropriately describes geometry in nature. Euclidean described by a usually simple formula, but in case of fractals, it is described by an algorithm. Discussion on fractals is kind of a never-ending story. The very way we have talked about the infinite levels of details that are built into these fascinating geometric patterns, the very way this discussion can also prolong for a long time. There are people who are working on this area, in this area, and on these ideas, and they are making more interesting patterns, the fractals. I hope that some of us would also be joining that journey and would be exploring the depths of this fascinating world of fractals. But we have to stop somewhere, so probably we are going to call it a day over here. But before leaving, let's briefly recap what we have talked about today. We have discussed the basic idea, the definition of the fractals, and how fractals are different from the Euclidean geometry that we have been living with and describing objects with. We have seen the difference between the Euclidean geometry and the fractal geometry as well. And we also have seen some examples of fractals. And we have come to believe and understand that how Euclidean objects can be defined mathematically, but in case of fractals, we have to have some algorithms that describe them. Although these algorithms are not very complex, they are quite simple, and simple to understand and simple to grasp, and then even simple to program as well. As I mentioned earlier as well, that we'll be able to see that even very, very complex patterns, fractals, just like the fern, can also be coded making use of very few lines of code. We'll try to take a look at that implementation aspect as well some other time. But for the moment, let's conclude it over here. So folks, I hope you would have enjoyed our discussion about fractals today, very fascinating and exciting geometric patterns, which are different from the Euclidean patterns that we have been dealing with and drawing objects with. I hope you'll be able to pick some inspiration and walk into further details of the subject, but that you can do on your own, making use of some reference text that is available, and we'll try to include some stuff in your class notes as well so that you can make use of it. For the moment, let's call it a day. Next time, we're going to come up with some more advanced topics with computer graphics. Hope to see you then. Ijazat dijiyega. Fi aman Allah.